Another concept related to solutions is that of colligative properties. And when we talk about colligative properties, we're talking about properties that depend on the number of solute particles. See, I had my highlighter out earlier. Let's pull it out again. Colligative properties depend only on the number of particles in the solution, the solute particles. Doesn't depend on the type of solute particles. So this is kind of a weird thing. Separate section here. So if we add a non-volatile solute, do you remember what volatile means? Explodes. Well, yeah. It evaporates easily. And if it's something that's flammable, it will explode easily as well. So add a non-volatile solute, something like salt or sugar, something that doesn't evaporate quickly. If you add that to a liquid, it extends the temperature range over which the liquid remains a liquid. So it lowers the melting point and it raises the boiling point. So we call these freezing point depression. I told you we'd talk about depression today. And boiling point elevation. No, go ahead.
That's why they add salt to ice?
Yes, that's why you add salt to ice, either to melt it or to make ice cream. And freezing, I just thought of this, it's amusing to me, you guys might not like it. Freezing point depression, that's what happens when there's a hard frost warning and the citrus farmers experience freezing point depression. No? One person liked it, that's okay. So these colligative properties depend on the number of particles. Okay, I think I kind of duplicated slides here. Anyway, adding salt to ice lowers the melting point. Okay, I grew up in Minnesota where they have a lot of ice on sidewalks, and it's dangerous. And, you know, people slip and fall and break bones all the time. So you want to get rid of the ice because you don't want to get hurt and you don't want to get sued. If you throw salt on the ice on the sidewalk, it will melt the ice, even though the temperature is not warm enough for the ice to melt, because the ice lowers the melting point of the ice. And that's the ice, the salt, thank you. I knew I was going somewhere wrong. The salt lowers the melting point of the ice. And that's the same reason you add salt to the ice when you make ice cream. Because ice, pure water, melts at 0 degrees Celsius. Ice cream melts at a lower temperature. And if you've ever tried to take popsicles or ice cream to a picnic by packing them in a cooler full of regular ice, you know that that's just not going to keep them hard. They're going to get soft and mushy, right? If you want to keep them cold, you can either use dry ice, which is a lot colder, or you can sprinkle a whole bunch of salt on the ice. Then the ice will melt at a lower temperature and it will stay colder. We also see this in everyday life as antifreeze. Why do we add ethylene glycol? Why do we add antifreeze to the radiator? Well, around here, we're not very worried about the radiator freezing solid. In Minnesota, it's a problem. If you don't have antifreeze and your car's not in a heated garage at night in the winter, your radiator will freeze and burst. Not good. Adding antifreeze lowers the freezing point of the water. It also elevates the boiling point, which is what we care about more around here. You don't want the water in your radiator to be boiling, because there's a pressure gauge on the radiator cap to keep the whole thing from exploding, but your fluid in your radiator is going to evaporate and get out. It'll escape through that pressure gauge, and then your radiator will go dry and it's not able to cool your car anymore. So that's not a good thing. So the ethylene glycol, which is the active ingredient in antifreeze, raises the boiling point so that it boils at a higher temperature, and that makes it work better. So we have some equations that help us to calculate the amount of freezing point depression. And to look at these, we have to think about a slightly different concentration unit. Molality. Okay, this word is really similar to molarity, right? One letter different. I am sorry. I don't like molality either. I think it's stupid. But here it is, and I have to teach it, so shoot me later. Actually, just shoot me now. Molality, and the symbol for it is a lowercase m. Yeah. See, you guys get it. This is ridiculous. It's a lowercase m, not to be confused with meters. Okay, meters is also lowercase m. That's a major issue if you ask me. So what is molality? Molality is moles of solute per kilogram of solvent. It just gets worse. Everything else we did, the percentages and the molarity, it was all about the volume or the mass of the solution, right? This one isn't. So this one is just wrong in every possible way. Maybe that'll help you remember it. It's just wrong. Kilograms of solvent. I'm sorry. It is what it is. So let's calculate the molality of a sucrose solution containing 50.4 grams of sucrose and 0.332 kilograms of water.They gave us the kilograms of solvent, so that was nice. So molality, I didn't mean to highlight, but I did. Look at that. Molality equals what? Moles of solute per kilogram of solvent. There is actually a reason that it is this way, but it's... Anyway, so what do we need? We need moles of solute. We need kilograms of solvent. Well, they gave us kilograms of solvent. Let's just go ahead and stick that in before we forget what we're doing. 0.332 kilograms. They didn't give us moles of solute. They gave us a mass. But that's okay. We can figure that out, right? Can somebody look back in their notes, just to save a little time, and remind me what the molar mass of sucrose is? It's like 342?
Yeah,
0.296, thank you. We calculated that earlier. We don't need to do that again. So they gave us a mass, so 50.4 grams of sucrose, and we're going to convert this to moles using our fabulous molar mass converting skills. Which, you know, about this time you should probably be able to do this in your sleep blindfolded. 50.4, typed in the wrong number, 50.4 divided by 342.296 equals 0.14724. That guy's got 3 sig figs. This is moles. So I'm going to stick this up here, 0.14724 moles. So I take that and I divide by 0.332 equals. And this will be 0.443 lowercase m. Molal. Any questions? Other than why? Because? So now that we know how to do that, this is the equation for freezing point depression. So delta means change. Remember that? The little triangle means change in. So this is the change in the freezing point. This does not tell us the new freezing point. It tells us the difference between the usual freezing point and what we have. So we may have to look something up. This M is the molality. The molality, and Kf is a freezing point depression constant. So Kf is a constant that is specific to a certain substance, a certain solvent. So if you're dealing with water, Kf is one thing. If you're dealing with acetone, Kf is something else. So this would have to be looked up. So calculate the freezing point of an aqueous 2.6 molal sucrose solution. And we're told that for water, the freezing point depression constant, Kf, is 1.86 degrees Celsius kilograms solvent per mole solute. Crazy units, huh? Those units actually are really, really helpful because we understand dimensional analysis. If we forgot the equation for freezing point depression, we can figure it out based on the units. So, two approaches here. We can use the equation, or we could figure it out from the units. What do you want to do? I can do both. I can. So first let's do the equation way. So the freezing point depression, delta TF equals the molality times KF, right? So what's the molality? 2.6. Very nice that they gave it to us. 2.6 moles per kilogram. And then KF is this guy right here, times 1.86 degrees Celsius kilograms per mole. And we see that these units cancel out. So 2.6 times 1.86 equals. This should have how many sig figs? 2. 4.8, and the unit will be degrees Celsius. Is that the answer? No. That is the change in the freezing point, not the actual freezing point. What is the freezing point of pure water? 0. Freezing point depression means that the temperature goes down. So delta TF is going to equal the actual freezing point minus, I'm sorry, that's not right. TF, the final temperature, is going to equal the true temperature, the regular freezing point, and we'll subtract the change because it's going down. So that means it will melt at minus 4.8 degrees Celsius. Any questions?
So when it comes to freezing point depression, most of your answers will be negative, right?
For water, yes.
For water.
If you're doing it with a solvent other than water, where its temperature is positive, freezing point, then it could be positive. The thing is that's important to understand is that the freezing point goes down. And I like how it describes it as the temperature range over which that solvent remains a liquid increases. So it bumps both of them away from each other. I used to have a hard time remembering which went up and which went down. But it's making that liquid range larger. That means the freezing point goes down, the boiling point goes up.
Would the boiling point go up by 4.8 as well?
No, because the boiling point elevation constant is different. That's another equation. Really similar, but we're going to switch the F to a B. That's a good question. It's a good question. So any questions about how I did this one? So let's look at the other method. Oops, that's not what we want to do. So we're going to look at this 1.86 degrees Celsius kilogram solvent per mole solute. And we're trying to find something that's related to temperature. right? A temperature change is what we need so that we can figure out what the freezing point is. So the unit that we want is in the numerator here. So that means we're going to leave this guy right side up, and we're going to try to get rid of kilograms and moles. And so we look at the other unit that we have. Let me see the other number, 2.6. The units on that are moles per kilogram. Well, what we want to do here is we want to multiply by moles and divide by kilograms, because we want to get rid of these units. And molality has those units in it, so we can just throw that in here. We're going to come up with the same answer that way, but we did it without using the actual equation. We did it by looking at the units. And that's one of the brilliant things I learned in high school physics. Our teacher taught us dimensional analysis and then showed us how we could figure out most of the physics equations from the units alone. You don't remember the equation? Just put things together so the units work out and you end up with the correct unit. And a lot of the time, not every time, but a lot of the time you'll get the correct answer. And it's a lot better than guessing. Okay, so boiling point elevation, same idea, opposite direction. So the boiling point of a solution when you add a non-volatile solute is higher than if you have the pure solvent alone. So the antifreeze not only prevents the freezing of the coolant, but it also prevents boiling of it in hot climates like we live in. So the equation, very, very similar. All that changed was the subscript. The change in temperature for the boiling point elevation is the molality times the boiling point elevation constant. And again, different solvents have different values of Kb. And the value of Kb is not the same as the value of Kf. So calculate the boiling point of a 3.5 molal glucose solution. Here we're given the boiling point elevation constant for water. These constants are not something that you would be expected to know. Okay? They would be given to you. I will definitely give those. So boiling point elevation. Pardon my mistakes there. Delta T boiling is the molality times Kb. At least these equations aren't really very complicated, right? The molality is 3.5 moles per kilogram. And we're given Kb 0.512 degrees Celsius kilograms per mole. .5 times 0.512. This should have, again, 2 sig figs. So the change in boiling point equals 1.8 degrees Celsius. That's the change. What's the normal boiling point of water? 100 degrees. So our new boiling point is the boiling point of the pure solvent. Are we going to add or subtract? We're going to add. The boiling point goes up, plus 1.8, so we get 101.8 degrees Celsius. You can also think about antifreeze. When you add antifreeze to your radiator, it makes the freezing point go down, makes the boiling point go up. You got to remember which direction these things are going. Any questions?